if that's okay. Now, I'm not kind of used to this format. We've run this once before. I normally deliver training. Anyone knows that's been to my training courses. I like to have lots of models and videos and pipe samples, and so this online version is something that we're getting used to. But I'll try and introduce as much of that as I can through the day, through the session. My plans for today are to provide an overview of the key principles behind the national standard that we've now introduced and what we had before. Provide a basic overview of the key difference between the old standard and the recently published BS 9295, which was published in February of 2020. Talk about the limitations of that standard, because for those of us involved in the committee, it's still a work in progress, and we're already working on the 2025 version, and I'll talk a little bit about that. What I won't be doing today is running through actual calculations, as it's simply not time. And that might be something for another day or in another way. But the key principles are the things that's really important to understand. So we'll get on. So general background, there's lots of different types of pipe out there, from brick pipes, pitch fibres in the past, GRPs, cast irons, ductiles, concrete, clays. They all behave in different ways from a structural perspective and serve different purposes. You can group them into pressure pipe systems. These are the pipes that work under pressure, your water supply pipes, your gas pipes, your pressurized sewers, or your non-pressure systems. And these are your sewers, your drains, your storage tanks, pipes that are empty most of the time or part full. So from a high level background, there are enough water mains alone in England and Wales to wrap around the earth 8.5 times. So the water and sewerage company's biggest asset sets are the sewers, and the second biggest asset sets are the water mains. And at the current rates of replacement, it will take 200 years to replace all the UK's water mains, and that's the replacement rate we've had over the last 30 years since privatisation. And it will take 1,000 years to replace the UK's sewers. There's two things we can take from this. One, we're probably not replacing, particularly the sewers, nearly enough, and we need to spend more as a nation, and that is certainly a debate and something we're pushing hard for the next stamp. But regardless of that, whatever we build is going to have to last hundreds of years, and we need to design these things with that in mind. Whatever this standard had to do, it had to work for 150 mil diameter clays all the way up to 3.5 meter diameter structured wall pipes and pipes running at 40 bars of pressure, which are all really different in all different ground conditions. So you're looking for something that's quick and simple and for small diameter, low risk pipes, while being fit for purpose for the more complex products that are out there. So there are lookup tables for your rigid pipes and your semi-rigid pipes, your small diameter stuff, which you can simply, if you've got Class F bedding, it'll tell you what clay pipes of certain diameters will do in main roads and elsewhere. So this is for a 150. So today's talk isn't about the simple pipes, it's about the pipes where you have to do some calculations, and the lookup tables don't cover it. So from a structural point of view, there are three fundamental classifications. We have rigid pipes. Now these are the pipes that don't bend and flex, something like a clay or a concrete. Ultimately, they carry the load themselves. They transfer it down into the ground beneath them. And ultimately they'll crack and break rather than bend and flex. We have flexible pipes. Now these things tend to deflect and form an oval shape when they're loaded, and they can derive a lot of strength from the surround around them. And then you've got semi-rigid pipes, and these are flexible pipes that are very stiff and strong, much stiffer and stronger than the ground around them. So they behave a bit like both. And so they're the fundamental three categories that we tend to break pipes into. And we'll explain a little bit more about that later. Okay, so structural design of buried pipes, some of the fundamental principles. Just play this video, and this is a rigid pipe, and all I'm going to do is load this rigid pipe up. It doesn't bend at all at the sides, it's being pushed down into the gravel, and then ultimately it cracks and breaks. Now if there'd been material around that, it'd have ended up supporting and looking a little bit like this, but that's how they fail. They crack and split So what's happening with this rigid pipe, and is it's there. That's it. This is a modelling clay as it happens. It's sitting in the bed. It's sitting in this gravel. Now, if that was a flat area, it would just be a point load there. So any loads above it get transferred into this. But it's carrying that load itself. It's developing moments in the wall, and it's transferring them down into the bottom. And the wider this is, the wider the area that it's transferring the load into. So if we take that out, the next one has like a sponge underneath it. So this is softer ground. And as we load the pipe up, it transfers the load down into the pipe underneath. And it squashes that. So basically, you've got the loads from the earth backfill and from traffic on top that's pushing the ground down into the ground below. So what's important is the embedment below the pipe, really. And it's having that foundation so it can spread that load out across the trench width. So naturally, as you'd expect, these are the rigid pipe embedments, and they focus on the section underneath the pipe. Now, I'm going to simplify this table a bit by taking out the narrow trench, and my advice is ignore narrow trench and default to wide trench. In certain circumstances, narrow trenches can offer some advantages, but there's certain things you have to understand about when a narrow trench is a narrow trench. So if we just look at wide trenches for now, what you have is you've got gravel. And so this is gravel underneath the pipe. It's still quite harsh under there. So this detail has a bedding factor, class N, of 1.1 to 1.3. If you just bed it better to a higher level, it goes all the way up to 1.9. If you bring it up to Springer level, the gravel, it comes up to 2.5. But if you go for full class S, and all the flexible pipes as we cover are class S of different types, it's very little difference. It's about what goes on underneath the pipe that really matters to a rigid pipe. And if you need to step it up further, there are concrete and reinforced concrete embedments that can give you bedding factors all the way up to potentially 5.7. So very simply, I won't labour it, you've got to work out a load, which is the soil, plus the load due to the water in the pipe, plus any loading from traffic. And there's guidance given on this. And the bedding factor that you get from here, so these bedding factor, if you select B, 2.5 has got to be greater than the total design load, which you just calculated, times a factor of safety divided by the crushing strength of the pipe. So the higher the crushing strength of the pipe, the lower this number becomes, and you need less of a bedding factor. And it's as simple as that, really. When you get onto the flexible pipes, I'm just showing this video. Now what I'm going to do is I'm going to drop a block of plastic onto this flexible pipe. And so this flexible pipe doesn't have a lot of inherent strength. So there you go. It's a big block of polyethylene, a sample from a 75mm thick pipe as it happens, but it works as a good block. What I'm going to do is I'm going to pour embedment around this now. Now this is a class S1 embedment, single size gravel, and it flows beautifully right round and right underneath the pipe, as I'm going to indicate. And that's the measure. This area underneath the pipe here is really important, and you've got to get a material that flows right underneath here. You've got to make sure material's right underneath here. So that's the class S1 material. Nice gravel. And there you go. 1 block, 2 blocks, 3 blocks, and it carries it nicely. And what it's doing is it's carrying that load. There's a compression of the pipe, and it's carrying it into the sides here and into the glass of the fish tank. So what I'm doing in the left-hand side now is I'm going to have the same pipe, same gravel, but I've got these sponges which are going to replicate, if you like, soft ground. So this is what you get is you had soft ground in your trench, and we'll see what difference it makes. So we're going to pour the gravel in. The soft ground's not behaving itself properly, but that's fine. So the gravel goes in, again, pours around. The pipe wants to move around, which is a problem in the real world with these things too. There is a skill to backfilling these, and if you want to lay them to fine gradients. So in it goes. We're now going to load it up. So the previous side took 3 blocks, and we're standing it no problem. So block 1, Block 2, and it's beginning to flatten and struggle. As I introduce the third block, down she goes. So what's happening here, you can see this is the point. Third block goes on, it begins to flatten out. It's pushed itself outwards at the trench at each side. The sponge hasn't given it enough support. And then as it flattens, it buckles down, and you get a complete buckling failure. So, okay. Hang on. So what I'm going to do this time is the trench is going to be the same. Same width, same pipe, same material. I'm going to use a sand. And the difference between sand and gravel is the gravel that was used before was self-compacting. It's a single-sized gravel. I can compact and bounce on that. It'll make very little difference. Whereas with sand, if you compact sand, it makes quite a bit of difference to the sand's density and therefore its behaviour. Now, when you work overseas, and it was quite an eye-opener for me when I was working in Germany and Holland and Cyprus, is the science that goes behind the whole compaction of trench materials. And they have laboratories on sites, and they're continually doing proctor density tests and testing the materials coming in that they're going to use as backfills, and then checking that the actual compaction has compacted it to the specified density. And it's quite a thing that goes on. In the UK, we've tended to use self-compacting gravels, and so we've not had the compaction issue. Now you've got to watch here, just as I'm compacting this, I'm doing it lightly, but the pipe's trying to ovalize. So compacting this heavily is actually quite difficult, both in real terms and for me in my fish tank. So we will fill it up. So this side's going to be compacted. And we move to the other side. We're simply going to put the sand in around the pipe. Now sands vary quite a lot, as we'll show. This is quite a good material for compaction. This does flow quite well, and it's flowing underneath the pipe quite well, but compacting this bit underneath can be really tricky with some of these materials, and there's special tools developed and all kinds that get used in nations, but I don't see used in the UK. So as we move to an era where we're being forced to reconsider the use of self-compacting gravels and try to use more selected as-dugs, the whole compaction issue and behaviour of these materials is something that I think we're going to need to get into in much more detail and understand to a greater level. And we need certainly to debate as an industry which way we want to go on this and how we deal with it. So as you've seen, I didn't compact this side a lot, but we'll see what difference it makes. This is good quality sand. This is uncompacted, and we're going to load this up first, and we're going to use a 2-litre bottle of water. So it weighs approximately 2 kilograms. I'm trying to place that in place, and over she goes. It's not going to handle that load. The compacted side, however, can. So just that bit of compaction has made quite a difference to support that the pipe is receiving from the surround around it. So natural ground matters around the pipe. The material and how you compact the material around the pipe matters. What we're going to do now is we're going to look at trench width. So we just play this video. So we've got the sample that we used before with the foam, and we're going to use the same gravel. And on the one on the left, we're simply going to have the same thing with foam, but it's going to be a wider trench. So this is just looking at trench width and the effect that the trench width has. There you go, that's the material. And we're then going to look at the pipe at the end, which is simply a stiffer, flexible pipe, and the difference that going for a stiffer pipe makes. So there we go, nice class S1 material. As you see, the pipe trying to move around as the material is poured. Material running beautifully and compacting underneath the pipe, which single-sized gravels do. We'll fill that up, and we're going to do the same. So these pipes are the same. The gravels, backfills are the same. The ground conditions are the same. The difference will be the width of the trench, and the one on the left being wider. have more of the good material before you get to the softer material. We'll add a little bit more into this, and then we're going to load them up. Okay, so we knew from the last experiment that this handled 2 plastic blocks, but it couldn't handle the third. And it would be no surprise to find that it's the same this time, but nevertheless, we'll load it up anyway. So that's first block going on, handles that. Second block goes on, it starts squashing the sides, and it's beginning to struggle and flatten. And the third block goes on, and she begins to struggle, starts to give, and then it there you go. Once it flattens, it just becomes, it loses its arch effect and buckles and fails. So this side, same gravel, same pipe, same natural ground, just a wider trench. Block 1 goes on, block 2 goes on, and it's moving, compacting this material. Block 3 goes on, and it's managed to hold it. And so the trench width also matters, and it's a way of strengthening pipes in softer ground conditions. So we're then going to put a really heavy load on what is a flexible pipe, but it's a much stiffer flexible pipe than was using here. So that's your 2 gram bottle, the pipe. So the stiffness of the pipe itself also makes a big difference. So what's happening is these loads are carried by a combination of the pipe itself, the embedment around the pipe, and the natural ground conditions. And it's the combination of the 3 that carry the load. And no matter where you go in the world, no matter whether you use the German standard, the French standard, the American standard, they're all based on these same principles. They might use different factors, different equations, but the principles are the same. So for the native soil, we take this Spangler modulus, E3, and this is the table that it comes from. It used to be the old table NA3, it's table 13 in the new guide. If you've got a clay, this Spangler modulus can be from 0 to 14. So if you've got a stiff clay, it could be 6 to 11, 4 to 10. And the engineer, the designer has to guess. There's no guidance, you simply have to guess. If you've got sand, it could be 20, it could be 1. You've got to guess at which is the appropriate figure, which is far from ideal, but that's what we've had since the 1940s. Module C2 is for the embedment, and you get this from table 14. It was the old table NA6. And class S1 self-compacting is there. If your class S2 is a graded gravel, if you go up to 85% compaction, you get an E2 of 7. If you want to use a sand, an S3, you've got to compact it to 90% to get an E2 of 7. And so what you do is you combine the trench width, this is your BDBC, your E2 and your E3 through Leonhardt's equation. And that can give you an overall soil modulus. And it's a combination of the trench width and the natural ground and the embedment properties. So for flexible pipes, they're all class S, full bed and surround. Very different to the rigid pipe embedments. You've got S1 and S2, which is your single size gravel or your graded gravel. And then your S3s to S5s are your sands or your selected as dugs. When you get to the lower quality selected as dugs, your S5s or your B1s and B2s, they're not for normal flexible pipes. These are only for the semi-rigid pipes or the really high stiffness flexible pipes. Once you've got that equation, that number, you can then run your calculation for buckling, and you can do your deformation ovalization assessment, and then you've got to calculate hoop stress in thermoplastics or straining GRPs, and the guidance is there, so we won't go into that today. Once I cover this is really important. So we have a ductile iron pipe here that's under pressure. This is 900 mil diameter, and the limit that the manufacturer says that you've got on the joints is a deflection of 3%. The joints can accommodate a 3% deflection. So that's the limiting factor. What we're going to do here is we're going to load this pipe up and cause it to have more than a 3% deflection. As it deflects, it starts to leak. So you see the leakage there. So it's not that the ductile iron pipe's going to buckle and fail as they did in the fish tanks. It's the fact that if you allow it to deflect by more than 3%, in this case, it's different for different sizes of pipes, the joint will start to leak. I'm going to take the load off it and the pipe recovers and it stops leaking. And put the load back on and it starts to leak again. Let me just ease the load back on shortly. So the limiting factor for a lot of pipes is what the joint can handle. And you've got to consider this for the gravity sewer systems as well. That's often the limit. It's not that they're going to collapse. It's just you get infiltration because the groundwater can get in because you've exceeded what the spigot and socket can cope. In other systems, it's the coating systems and lining systems that can start to split and crack if you allow the pipes to deflect too much. So you've got to know what the limit is for your pipe system. I'd love to give much more guidance on embedment selection and embedment assessment because it's quite a big area and it would take me all lunchtime just to cover the basics of it. But it's an area of growing importance. How do you know that the material you got is suitable? And it depends on your pipe, it depends on your ground, it depends on the material, which vary quite a lot. Two of the guides that I think are quite good, but we'd like to do more work with Information Guidance Note 40801, which is freely available on Water UK's website, and Water Industry Standard 40802, which give a lot of guidance as to what's suitable and what isn't, and how to assess selected as ducts. We think there's more work to do here. We've included things like the compaction fraction test in the new 9295, but as we get pushed harder and harder in this area, I think we do need to do more work to back up how it goes forward. But there is quite good guidance freely available there. So in summary, we have a separate structural design passage for rigid pipes. This is your concretes and your clays, your cast irons, your flexible pipes, your steels, your reinforced polyethylene, steel reinforced polyethylenes, your PVCs, GRP pipes, and then your semi-rigids. And there's three separate, if you like, design guides for each of those. So why are we changing the standard? Well, structural failures of pipes are not unusual, and we're under big pressure to save money and under increasing pressure to minimize waste and reduce embedded CO2, and that is only going to increase. The question that's been asked more and more is, do we need the imported embedment? Well, you've just seen just how important embedment can be. It's a key part of the structure. If we don't need it, then clearly we shouldn't have it. It's a waste, and that's wrong. If we do need it, building pipes twice is not good for the environment or anybody else. So it's really important we get this right, and really important that we give the designers tools. It's also noted that a lot of pipes are getting thinner, and again, in the name of the environment, which works in some conditions but not in others, and you've got to make the right judgment call. We're also playing with some really big pipes, and so we've got thermoplastics now available and being used, anything up to 4 meter diameter. And they're being used as storage tanks. Like this example, and very successfully in many examples. A lot of thought's gone into this. You can see where the earth has been stockpiled a long way from where the excavation is, and where the routes for the traffic is, so they're not trafficking over the pipes. Also, this excavator sat on a lot of earth as he's backfilling progressively along the length of the pipes. So he's not loading the pipes excessively or in an uneven way. So a lot of thought has to go into how you build these things. If you put the thought in, they work perfectly well. If you don't put the thought in, they do deflect. And this particular one was caused by a large excavator tracking alongside the pipe before it was fully backfilled, and so the damage was done, straight away. If you get them right, some very large structures have successfully gone in the ground. This is Beckton outfall, but there's a lot of clever engineering went into that, and it works. But it worked because it was planned very carefully and engineered very well. All kinds of products out there. This is a polypropylene towards the left. Say you've got your steel reinforced polyethylenes, you've got your whalites, being used successfully in a lot of locations. Do things right, they work. If you do things wrong, as with any pipe systems, they don't. So what have we had? Well, back in 1997, BSEN 1295 was published, and it was my former boss, I'm pleased to say, a real gentleman and an excellent engineer called Jonathan Olive, who wrote the British element of that. In many respects, it was a failure, and it was a failure to unite the whole of Europe behind a single method for designing pipes, buried pipes. When you think about it, there's good reasons why a lot of our European neighbours have developed different methods to us. The fundamental principles are the same, but if you go to Holland, Holland is, well, it's the delta, so it's all under, you hit the groundwater table straight away, it's either peat or sand. So they've become experts at compacting sands in those conditions and using sands as backfills to pipes. We use gravels, we're an island nation, and so we've tended to use gravels. But the fact that it became a collection of, hints as to how the different European nations designed buried pipes meant that it was limited as to what Jonathan could put in. So all the formulas were in here, and what Jonathan then did was he started to write a guide to the structural design of buried pipes. And after he sadly passed away, Sandra Ralph Dickinson picked this up and worked with BSI and an excellent committee of people. And in 2010, they actually published the guide to the structural design of buried pipes. So what we had prior to the latest revisions was all the formulas and key tables and data for the UK in 1295, and all the guidance and explanation in 9295, and you had to buy both documents. What we have now is 1295 2019, which all the UK elements and detail has been taken out of. But if you're going to work in Europe, it gives you an overview of how each European nation approaches the structural design of buried pipes. However, if you're only working in the UK, everything that you need to follow the UK standard is now in BS 9295 2020. So if you purely work in the UK, this is the one that you need to buy. I'm going to mention this one, which is a very important document, but is not well known. This is BSEN 1610. And it underpins all the standards as far as pipelines are concerned, because it outlines the assumption of how things will be built. And if the pipe or sewer has not been built to this standard, in accordance with this standard, then a lot of the design standards don't apply. And you've got to be very careful. So things like minimum trench width are very clearly spelled out in here, and all the design guides, including the structural design of buried pipes, assumes that this has been followed. And if it's not followed for whatever reason, then you're outside of the standard. You've got to be very careful. So we'll come on to this again a bit later. So why have we changed it? We wanted a single standard that was easier to follow. We needed to tackle the larger diameter pipes and make sure that was addressed properly, and tackle this challenge posed by, do we need the embedment, and provide perhaps better guidance on that. We had to keep it simple and easy to follow for small diameter and low risk systems, but fit for purpose for all the products that we're actually using today. So how was it set up? Well, there are a few early chapters that give you a lot of description, a lot of background knowledge, and a lot of the sort of areas that I've been covering today are covered in that. Clause 5 covers the classification of loads and how to calculate the loads. And then if you've got a rigid pipe, all you need is clause 6. You don't need anything else. If you've got a semi-rigid pipe, you skip clause 6 and 7, you go straight to clause 8. And everything you need is in clause 8. You don't need to cross-reference. And if you've got a flexible pipe, all you need is clause 7. Now, one of the key differences that we have within clause 7 is that we have the old Marston-Spangler method, but we've also introduced a new Gumbel method, and we'll talk about that in a little bit. This Gumbel method, for now, it's been primarily aimed at thermoplastic pipes. It's based on research that Dr. John Gumbel did back in the 80s and 90s for the highways, and a lot of the highways tables are based on his theory. And it's basically a better model, certainly for how soil behaves around thermoplastic pipes. The old Spangler system had been originally developed around corrugated steel pipes. So it's primarily aimed at structured walled and solid walled thermoplastic pipes. This is your polyethylenes, your polypropylenes, your PVCs. We're recommending it for anything above 900 mil, although it can be used for smaller. It takes accounts of non-pressure systems. It's not for pressure pipes. And of course, with all the others, it assumes that the trench has been and the pipe laid in accordance with BSEN 1610. So that's a big difference, and we'll talk a bit more about that later in the next few slides. The biggest single change that everyone really needs to be aware of is that for all flexible pipes, whether using the Master Spangler or the Gumbel method, there's a new factor of safety that must be added to the deflection calculation. What we were finding is that buyers were buying the cheapest pipe with a stiffness of, say, 2 kilonewtons per meter squared, which is fine if you get everything else right. But then they were buying the cheapest embedment they could get hold of and giving it to the cheapest contractor to build. And that wasn't ending well. And this is what we felt we needed to stop. So we've called that a type C, where you use a class 2 embedment and you have unmonitored installation. And if that's the case and you've got an SN2 pipe, you've got to add 5% to your deflection. Now, given that deflection allowances range from 3 to 6% from jointed systems and 8% for welded systems, that means you're probably going to fail in design, and so you can't do that. If you want to use a stiffness of 2 and you want a small factor of safety, then you've got to have installation monitored by either the pipe supplier themselves, so they can warrant it, or by a lot of these have been built by developers, so the water company might say, well, pay us to monitor this installation, and you can use the cheaper pipe. Alternatively, you can use a stiffer pipe, in which case your factors of safety are far less. Now, this applies to all diameters and all flexible pipes. Given that most small diameter pipes are SN8 or above, this shouldn't be a big problem. But the larger diameter pipes, it's not a problem. It allows the designers to say, hang on, you can't do this, and to limit the failures that were occurring. So the Gumbel method won't go into a lot of detail. In principle, it's looking at what would have been a particle of soil and the behaviour of a particle of a soil that if the pipe and the trench wasn't there. So if the pipe was missing and you had soil in its place, how would the stresses on that particle of soil behave? And it looks at the uniform distortions and the distortional loads, and it comes up with like a total load. Principal deformation modes are compression, because the loads can become so great on these that the walls of the pipes can actually begin to crush. If it's very stiff, you can get settlement into the base of the trench, and then the ovalization that we've covered is more typical. The pipe properties that you need are the plane strain modulus of the pipe material, which the manufacturers have to provide, the flexural ring stiffness of the pipe, and the compression stiffness of the pipe ring. Other than that, the principle is the same as the Spangler method. So you've got this overall soil modulus, which takes account of the native soil and the pipe embedment zone. So this MSB value comes from the embedment, and this is compaction, and it gives you figures. You know, S1 self-compacting there, S2 with different compaction levels here gives you the figures. For native soil now, you get this MSN figure, which feeds down into this soil support factor. The difference here is that the actual MSN figure comes from soil data. So if you've got, for granular type soils, a standard penetration test result, you can read off the figure rather than guessing one, which we believe is far better. If you've got cohesive soils, then you're looking at a compressive strength of the cohesive soil, and you read the figures off, and that feeds into this. You've got MSB from over there, and that gives you your SC value if you know your trench width. So your trench width's built in, and then that comes up to form, you know, your overall modulus, which is dependent on trench width, embedments, and natural soil. Same principles, different way of arriving at the numbers. So the Gumbel method more accurately describes the structural behaviour of large diameter circular thermoplastic pipes. Soil properties no longer guessed. As you say, you're getting them from actual test results. It's less complex than the US version of this and what they've introduced. And that's largely because the European product standards are higher than the American product standards, so we were able to simplify the calculations. But this initial factor of safety or initial deflection should have been applied to all calculations since February. So if people are not aware of it, you need to be aware of it. It needs building into whatever spreadsheets the consultants are using. So there's also a lot more guidance on there, which is a double-edged sword for consultants, because if the guidance is there, you should take note of it, but there which can help you, and so you need to look at it. There's more guidance on embedment selection, includes now the compaction fraction test, but we would like to do a lot more work here and include testing as we're going forward as a BSI committee. We've included guidance for all void sewers, which wasn't there before. There's more guidance on the longitudinal aspects, but there's much more work needed here as well. There's some guidance on the use of recycled materials, but again, I think more work is needed as we move forward. A few things I'd just like to touch on, and I know time is getting short, is the importance of EN 1610. When you look at deeper pipes, often in bad ground, you sometimes need to support the trench with sheet piles rather than trench boxes. Key assumption behind EN 1610 is removal of trench support system should be carried out progressively during the replacement of embedment. Removal of trench support system at the level of or below the embedment after the main backfill is placed can lead to serious consequences. So the assumption in 1295, the standard 9295, the standard calculations is and always has been that the trench support will be removed progressively. If you're going to remove it all at once, it's a problem, and it can cause a high load case. Now, there's some guidance in this in Annex A, but it's often necessary to leave parts of the trench support in place. And again, this is a subject in its own right. If you're on piles, I'm not a fan of putting pipes on piles, but if you are, again, there's additional factors need taken into account. If you're directional drilling or tunneling, this isn't the right guide for you, and there's guidance elsewhere that you should take account of. When you're doing multiple pipes in single trenches, there's guidance there, but I would highlight that when it comes to EN 1610, there's an assumption that if you've got a pipe that's greater in diameter than 700 mil, you should have at least half a meter between pipes. And I see systems where there's as little as 6 inches between 2 meter diameter pipes, which makes it impossible really to ensure that you've got the right quality of construction, and impossible to maintain these things properly. And certainly in some nations, they look at much wider than the minimum expected in EN 1610. So this is a debate we need to have as an industry. You also need to take account of uneven loading. Big loading on one and not on the other, particularly as you're backfilling, things will distort and it will load up the pipe next to it. Equally, if you dig out one of these, it can cause a collapse if you leave the load on it, on the one adjacent to it. We see pipes fail at the foot of new embankments. As the ground settles, there's a lateral load can be placed on the pipe, and people have to be careful where they place the excavated material, as this can do the same and cause pipes to overlies the other way around. Trench base, very important that the trench base is good and firm. And what I say to people is that you've got to dewater, and you can't lay pipes in yogurt and soup. You've got to have a firm base. So in this case, you cannot lay a pipe in conditions like that. You've got to improve it. So what we have here, and we'll play this video on a bit, is this ground was being dewatered. So this was a real challenge. This was a marsh at Barrow, where we had to get the pipe, and we did get it in. But the clue is here. This machine and these people are sat quite happily on this road that they've put in place for trafficking along. Now we'll play this, that's the ground conditions. So we had to bring geotechnical engineers together and look at a whole series of options as how we're going to get the pipe in here and get it to stay in put while we backfilled it successfully. And one of the options is to build your road underneath the pipe. What the principle that works for an access road also works for the base of a trench. If In other conditions, wrapping into RAM, particularly PT conditions, can work very well, and it depends very much where you are and what the loads are. We've got shallow installations. People like to pour concrete round pipes. Well, that causes a lot of failures unless you're building some sort of flexibility. A better way sometimes to put reinforced concrete, precast concrete units over the top to spread the load. So shallow buried pipes is an option, but if you are going to use concrete, there's guidance in there, and under certain circumstances it is necessary. We don't cover longitudinally issues very well at all in the standard, and it's something that we're going to work on. Rocker pipes are mentioned, but really it's two-dimensional. It's about the cross section. Longitudinal isn't covered well, and you need to keep your wits about you as a designer on that. The maths can be quite complex and appears comprehensive, but it's based on the SI. What do you really know about the ground that you're working with and how it's going to be built? A lot of guesswork can go in there. What about hard spots, pipe crossings, buried walls, chambers, boulders? They all can be point loads on your structure. How much you know about the natural ground? Construction methods are key to design. You cannot, you have to make assumptions in the design, but you may have to revisit your designs once you know how the contractor is to be built it. And the contractor needs to know what you've assumed. So he needs to know it's changed, and that needs to be clear. And certainly I do a lot of work in arbitrations where there's disputes, and arbitrators tend to take a dim view of designers who haven't communicated this sort of assumption well to their contractors. As you say, this is a photograph I like. It's Dale Street in Liverpool in the 1930s, a pipe going in, which is still in, but the tram lines and all kinds of other things and obstacles it's crossing and other pipes, there's a lot of hard spots along there that need to be taken into account that this design method doesn't take into account. The designer's judgment is needed for that. So it's new installations only. It's not conclusive proof that it'd be okay. You need engineering judgment. And these code documents help inform decisions. Sometimes big factors of safety are necessary if you simply don't know. So hopefully that's of some use. Sorry it's run over a little bit. Thank you all for your time. I think Norman might have some questions now.
Yeah, they're not all mine, Phil. You're all right.
Okay.
Yeah. Afternoon, everyone. I'm Norman Howell. I'm the CEO of the Guild, and like welcome you all to this seminar. And I'd also, on your behalf, like to thank Phil for that run through of the new standards and also some key sort of factors to take into consideration when you're designing pipes. So thanks very much, Phil. That was a really good presentation.
It's a big subject in 40 minutes. Yes, I'll do my best.
Absolutely. So there are 2-3 questions. The first one comes from, and I apologize, it's Ansha P. This question concerns 160 mil OD P100 SDR11 pipe, which is a pressure main. And the question is, it's be laid on ground covered with an earthen berm, and it's got natural earth covering the P pipe with about 100 millimeters of cover. And the question is, do you think this would be enough to take a pedestrian load?
It probably is my gut instinct. I need to have a proper look at it and just see what the detail is. I've done my best to picture it in my mind, but as you say, an SDR11 P100 pipe is a pretty stiff pipe, particularly if it's under pressure from the ground. It's more second comers I'd be worried about, and you know, people digging it up in the future, or if somebody wants to park a truck on it on the if it's on a footpath that you might have to be more wary of. In terms of people walking on it, if you get hold of a piece, it's pretty strong stuff, and as you say, whilst it is a flexible pipe, a 160 mm SDR11 is quite a stiff pipe and can take quite a lot of load in its own right.
Yeah, you also go on, sorry, I missed the last bit of the question, asking whether you feel it might need some lightly or high compaction and for the surround and the embedment.
It depends what you're using. Whether if you're using a self-compacting material, no. If you're using something like a sand, yeah, compaction certainly helps as long as you don't overdo it. You do a lot of damage over compacting, and this is a balance you've often got to achieve. Certainly with the more flexible pipes than you're dealing with in that case.
Yeah. The next question comes from Kieran Riley, and this is a simple, straightforward question. What guidance would you recommend for the design of pipe jacked or directional drilled pipes? So I guess he's asking what standards would apply here, Phil.
There's quite a bit of guidance out there, standards, which I don't know the numbers off the top of my head. I need to just go and dig them out, but there is separate guidance from that that's published by different people, and there's the separate European standards for pipe lining and for no dig methods. So there's a whole series of separate documents and standards that cover tunneling and no dig construction. And it might be helpful to put a list together, and then it's comprehensive rather than send you the wrong way really on that one. But it's not this document.
Right. So now the next question comes from Greg. Sorry, no surname, and it says, can the method for determining the native soil, and in brackets by site investigation, also be used for other methods of structural design, or should it also be used when following the Gumbel method? So I think what we're saying there is, can that sort of those tables be used for the other structural design method as well as the Gumbel method? I think that's
the simple answer is no. No. This is for pipes. It's been developed for pipes, and I would stick to that, and use other structural design for and other guidance which is out there for other types of structure.
We've now got, this is actually a comment from one of your fellow BSI committee members, Sandra Roth Dickinson, who you actually mentioned in your presentation. Good afternoon, Sandra. So she says, a great presentation, Phil. I think it's worth noting that whilst the Gumbel method is currently to be applied to large diameter plastic pipe, it is the intention in time to ultimately widen its application to all pipe materials and sizes.
And Sandra's spot on, and that's definitely the intention. It's a better model, and we just want to gain confidence and get feedback from its use in this version of the standard, so we can broaden its use hopefully in the next standard, the next edition of it.
Yeah. So our next question is from Thomas Sarrington, who asks, can the guidance be used to back calculate if an existing pipe is suitable under a change of loading condition?
A lot of the principles can, but the guidance is set up and the procedures are set up around new pipe installation. So there's some of the principles apply, but a lot of the loads come from the behaviour of a newly backfilled trench. And so you've got to understand where some of the loads are coming from and how that will vary. So with great care, and you've got to understand the standard quite well to be doing that. It's really set up around new installation.
Yeah. Okay. Thanks. Another question from Greg. When undertaking the design of steel pipes, they can fall into the flexible or semi-rigid category. I understand this is down to individual projects and in brackets, site conditions, wall thickness, etc. Should both the flexible and semi-rigid design methods be followed?
It would do no harm, and they're very similar anyway. So it's how stiff the pipe is compared to the ground around it is the key, and that's what. If the pipe is a lot stiffer than the ground around it, it falls into the semi-rigid category, and if it's not, it's more flexible. So a lot of the steel pipes used in the water industry tend to be flexible, but as you say, they can span the two. It does no harm to do both, and see what difference it makes, but I don't imagine it make a lot of difference. It's just you're adding to the checks that you're doing.
Now a question from Gareth, and this is Can you indicate what geotechnical testing is required to determine if a granular Site 1 material is suitable as a backfill material, the S4, or where this is specified?
Right, so if you look at the IGN and the WIS standard that I highlighted, and that they are both, well, we'll wander up to them. They're both freely available. You don't have to pay for them from Water UK, so you can get hold of these standards, and these might not be the very latest ones that I have. And that's a subject potentially for a future, but it's IGN 40801 and WIS 40802. These two guides do give you an idea from gradings as to whether the material is suitable. And it also includes, as does 9295, this compaction fraction test, which you can put the material through, which will also give you an indication of the type of material you've got. So my advice is get hold of these guides. They're not hard to follow. It's the best we've got at the moment, and they're not bad. They are definitely useful guides. We would like to improve them because we've got to start looking at all kinds of recycled materials, as we suspect, as things go forward, and liquid backfills, and it's not a world that's getting less complex, it's a world that's getting more complex on us.
No, that's good. So then our next question now is, let me see now, it's from Richard, and he says, it's a great presentation. You demonstrate the importance of understanding the geotechnical parameters to the successful design of the pipe. You showed SBTs for stiffness. Does the standard give recommendations for geotechnical laboratory tests, in brackets, e.g. compaction tests? I'm thinking parameters for design and also for confirmation during installation. Sorry about that.
You'd be stretching to EN 1377 for a lot of these sort of tests and compaction, it's a debate we need to have. If you go to Europe, this is a big industry. The whole compacting backfills thing is standard, and as you said, there's laboratories on a lot of sites where they're continuously doing proctor density tests, and then going out to site and doing compaction tests, and there's various available. If we do want to move away from nice imported gravels, then that's a world that we probably need to enter, particularly if you're using the more flexible pipes. And I don't think we're used to it in the UK. And when you get into selected as dogs, it does become quite important, and it's a debate we need to have as an industry. But there are standards out there, and it's all to do with fills. It's the same sort of test you would use if you're using a fill. So if you go on a big job where they're filling a great big hole in, these are the tests that are done, and there's labs on site, and this is how it works. It's just not what we're used to when building pipes, and perhaps we should get used to it, and that's a debate we need to have as an industry.
Just Greg came back after your last answer. I think we probably covered it, but he said, sorry, I meant the rigid, semi-rigid methods of structural design for pipelines, which currently use assumptions for determining the native soil properties. So I think you probably have covered that now.
We're still on Spangler, and you're still guessing for those. And do a range, and it informs a judgment, and that's the approach. It's not a definitive answer, it's a judgment call that has to be made as to which way you go. And
our last question now is from let's see, I think it's Latte, and it's excellent presentation, Phil. Some of the large diameter plastic pipe manufacturers that specialize in storage options use different types of strapping systems for preventing floating of the pipes. Does the standard consider these types of scenarios, or is there any guidance to be aware of?
No, it doesn't, but I accept that you're right. And as you saw when I was trying to backfill the fish tanks and the middle pipes in there, the pipes do move around quite a lot. We've given additional guidance on flotation in this standard, which wasn't there before, but this isn't flotation. What you're saying, when you're backfilling, holding the pipe in place and keeping it round. And then people say compact to 90% without 95%, sometimes without realizing what that means. It can be very difficult to do. And so no is the answer, but should we and could we? BSE in 1610 is up for review now, and we're re-looking at BSE in 1610, and that might be the place that we look to improve the guidance on construction and these sorts of things. So it's a good point.
Thank you. Okay, so I think we've come to the end of the questions now, Phil. So again, I'd like to thank you for your time and providing an excellent presentation. And I'm sure everybody's enjoyed it. To everybody else, I'd like to thank you all for attending this Pipeline Industries Guild webinar. And as Phil said at the beginning of this presentation, I'd like to remind you that our programme is ongoing, and details of all the up and coming webinars are on our website. I think the one we've got next week is going to be given by R2M, who are going to talk to us about pipeline fittings. And then, as Phil mentioned, we've got the Guild Goes Green conference at the beginning of December. And then you'll have the opportunity to question me a bit later in December when where myself and the Guild chairman and his deputies give an overview of the last year. So without any further ado, I'd like to close this webinar now. Thank you for attending, and I look forward to seeing you on some of our future webinars, and hopefully eventually in person, get back to face-to-face meetings. Thank you very much.
Thanks, Don. Cheers.
Cheers, Phil. Thanks.